Hey YouTube, Accomplished the Impossible here, and I have a video coming out today of the very requested commentation of a cell site video. I did a cell site training structure video a while back that was kind of just me walking around with the camera, showing what the cell site looks like up close and personal. I had a lot of comments asking, hey, we want to see a narrated version of that, so today we're going to do that. I do want to also say thanks again, everybody, for watching all my videos. I appreciate the comments and the thumbs up and the likes, and I posted a couple of shorts here and there, so try to do my best on both fronts. Once again, if you guys like this video, I would appreciate a thumbs up just to let me know if I'm actually doing something right. If you have any questions, put it in the comments, and better yet, that Discord there is there for a reason. If you guys want to join the Discord server and ask questions live or voice chat, whatever, I'm usually in there. Some days I work from home, so I'm monitoring it. I try to get back to comments as quick as I can. I can't always do it. Just everybody's got lives. So uh, that's the deal. I hope you guys enjoy the video. It's going to be a lot of information, a lot of head explosions, so I'm going to do my best to explain everything. But strap in, enjoy the ride. Okay, guys, hang in there. This is going to be a lot of talking and describing what things are on the towers and how they work, but y'all wanted it, so here we go. Okay, so in front of us, this is a pretty simple cell site build. This is a mock-up of an AT&T site, and we have several different things going on here. So the first thing, building up the basics, is cell sites are always comprised of three sectors. We have alpha, beta, and gamma. Different sectors face different directions. The sectors face, for example, alpha, it would be 0 degrees. This is the alpha sector on this particular site. Beta is 120 degrees, and gamma is 240 degrees. And those different azimuths are the ones that actually design or implement the RF layout and the RF pattern on the cell site. We'll go into a little bit more detail on how all that works later when we get a little bit more advanced in the description. So cell sites are three sectors. That is also where the term triangulation comes from. If you have three cell sites all communicating with each other and you have users on that cell site talking with data, that is where you would triangulate a location or pull GPS data from if you're driving in navigation, what have you. So, like I said, in front of us, this is the mock build. You can see the tower here. This is just a three-legged tower that normally would have been a guide tower, but it's just a single section for training. And then on the towers themselves, this would be a two-position setup. So normally you have 4 positions per boom. This big arm here with these horizontal pipes is called the boom, and you would have position 1, position 2, position 3, and position 4. So 1 and 4 are always your outside antennas, whereas 2 and 3 are your inside antennas. Normally, we would have the boom fully populated in most scenarios, where at least it was 1, 2, and 4, or 1, 2, 3, and 4. So it just depends on what the RF configuration is for that particular site. Okay, looking behind Alpha Sector Position 4 antenna, we see a item which is called the RRU, or Remote Radio Unit. This radio unit is actually completely isolated from the shelter aside from fiber. So nowadays there is no coax going up the tower anymore. All of the coax is jumped out from the bottom of the radio to the bottom of the antenna. And that saves a lot of money on lease space, and it also saves quite a bit of weight on the tower. Instead of having all these big 1 5/8" lines going up the tower, now you just have a fiber optic cable and some power trunks, and it's just way lighter for everybody, and way less headache for the structural engineers. But RRUs are extremely versatile pieces of equipment. These things have massive heat sinks on the back of them. Like, for example, this guy right here, these little fins is a giant heatsink built into this. These remote radio units are all-in-one units that are comprised of microprocessors, onboard monitoring systems, RF transmitters, RF amplifiers, receivers, cavity combiners, um, filters. They just have so much equipment in them, and it would take you hours to actually go through each individual part inside of these radios. These radios particularly weigh about 30 pounds a piece, 20 to 25 to 30 pounds a piece. This particular model is a RRU 32B2, which is a 1900 radio. In the cell industry, you have different bands. So you have 1900 or 1.9 gigahertz, which we just call 1900. You have 2300 meg, and then you have 2100 meg, and then you also have 850 and 700, 720 range, and the new FirstNet system would be 758. So there's a lot of different bands that the telecom companies own and use. And these little guys behind the antennas that are hiding are pretty much running the show and controlling all of the data. And this is one of the items that you physically talk to. And I guess the most simple thing to explain this is honestly, this is just a really big media converter. And what it's doing is it's converting a fiber optic data signal to an RF signal that can be transmitted wirelessly through a radio accessible network. So if we think of this as a giant media converter, it just makes the math a little easier and how everything works. Okay, another big important thing about cell sites is grounding. It's probably the most important thing on the cell site because if the cell site's not grounded, you're going to get struck by lightning and you're going to break all your equipment. Cell sites usually don't withstand a direct lightning hit. But the idea is if everything's grounded correctly, you're preventing static from building up on the equipment, thus preventing a lightning strike from even thinking about hitting the tower. Sometimes it's inevitable and you can play all your cards right and still get struck, but it's best to just do as much as you can to prevent that from happening. Okay, so this is a interesting point, interesting part of the cell site as well. I won't go into too much detail on this, but this is called color coding, and this is how you identify what each coaxial jumper is carrying. So, for example, just in the description on this antenna, we have a lot of different jumpers coming up here, and we'll start from left to right. So left is red, red, red. The the way that this works is the first band on the jumper closest to the connector is the sector identifier. So for this example, we said that originally earlier alpha is this sector that we're on, which is red. So alpha will be red, beta is blue, and gamma is green. So if this was and then gamma is the one at 240 degrees, and then this one is the 0 degree sector. So again, red is alpha, blue is beta, and green is gamma. The next band symbolizes or identifies the frequency that these jumpers are on. So for example, this particular jumper is we did identified as alpha. The next band is red. Red identifies as 700 megahertz. And then yellow identifies as 1900 megahertz, and orange is 850 megahertz. So that is how you identify different bands. There's different color codes for different things. 2100 is white, 2300 is brown, and then there's a particular one that was made for FirstNet, and I can't remember off the top of my head what that color code was. It's been a while. So that's the second band. The third band is the polarity. So for this example here, we have the last band here is red. So red is positive or positive port 1, orange is negative port 2. So you have 2-port radios and then you have 4-port radios. For the 4-port, it would be port 1 positive is red, port 2 negative is orange, port 3 is yellow positive or transmit, and then port 4, white, would be receive or negative. So, and all these would line up to the connector indications on the bottom that also show that there are positive and negative ports. And that's just basically means that these are going to antennas inside the panel antenna that that are specifically tuned for transmit and receive, and they keep them isolated. So this is a good look of another side of the radio here. This radio is again 1900, and it looks like this is on the gamma sector, which is green. I think that's green up there. 1900 being yellow. But these are pretty slim radios. I kind of like the way they look. I actually had a few in the house for a little while. They were waiting for them on a project, and they made really good little fireplace mantelpieces. So they look pretty cool. These radios have been discontinued. These aren't used anymore. These are being phased out by these guys right here, and the reason is this is a mono band. It only does 1900 meg, whereas this is a dual band which does 1900 and 2100. So the radio itself is a little bigger, but it does more for less weight. So that was a big game changer for the industry because now they could put a radio up on the tower with less weight adding to the tower. Why not? And then the only caveat to these things is they are power-hungry radios. They need a lot of power to run, and that kind of started another problem that we'll get into here in a minute. And then the one behind it is another dual bander, but this one behind it is a 700 and 800 meg dual band radio, which also has just normal 4.3 mini DIN connectors on the bottom. A mini DIN connector is a connector that looks similar to an N-type, but it is the newest industry standard out there. Second newest, I think the next one up, the next generation is the micro DIN, but mini DIN is good up to 6 to 7 gig, I believe. And small connectors, and they're pretty durable. Never usually had a whole lot of problems with them. Okay, this is another really important part of the tower. This is called the Squid or the DC-6. These come in different variants. So what these essentially do in simplest terms is these are giant surge protectors designed for DC. So from the shelter, you have 48 volt DC trunks that carry 3 circuits to the Squid. And we call them squids because they look like squids. So I'm going to call them a squid because that's just what I'm used to. But we would have, if you took this off, this dome cover, there is there are 6 strike zorb arrestors, which we'll see a little bit more in detail later. And they are responsible for arresting and diverting stray voltages directly to ground. They have giant solenoids in them that will connect over and create direct short to ground. So they divert lightning or surges of power into the tower steel and frame into the ground, going down to the ground versus going back down to the shelter and blowing out all the equipment inside the shelter, because you want to try to isolate everything as much as possible in the event of a lightning strike. So this is the Squid lightning arrestor, and additionally, not all models, but some models have a dual use. One side is the lightning arrestor, the other side is a fiber optic patch panel, and that is used as a transition point from the fiber trunk that comes up from the shelter into the back of the Squid, and then it jumps out individually to each radio. And each radio takes two fiber optic jumpers for redundancy and bandwidth needs. But so you have a lot of different variants of these things. Verizon has their own, AT&T has their own, T-Mobile has their own. It's just a whole lot of different versions of them, but they all do the same thing at the end of the day, and they're all just big lightning arrestors. And this, for example, is the beta sector. We'll get into more of that here in a second. So here's a better look at what the connectors look like. I know it's kind of dark, but these are Minidin 4.3 connectors. They look really similar to N-type, but they're not. This particular jumper, all these jumpers here have an issue. For any of you that knows tower industry, the tower world, the issue would be that the sector identifier band is missing, which should be blue for beta, and that is completely missing. And we purposely did that in training to kind of trick the candidates or the trainees and the green hands to identify different problems on the site. So not only did they build the site perfect, but the instructors and myself would come back out and make mistakes here and there, and they were responsible for coming out and judging on the tower to see what mistakes were made and what things needed to be fixed. And it was a great learning idea and a concept for them. Okay, so here is the ice bridge, and the ice bridge is pretty much what it sounds like. Below the ice bridge are these little trapeze mounts that are responsible for holding the cables that run in, and again, these are the DC trunks coming off of the tower along with the fiber optic trunk. This particular fiber trunk is an 18 pair fiber, all LC connectors on both ends. And the ice bridge was so that ice and snow and any other material would build up on top of the ice bridge and not fall on the vital communication lines going into the tower. You didn't want an icicle or any big slab of ice falling on a fiber optic line and shredding that to pieces or severing it in half.
Oh, big stuff, David. Big stuff. Big stuff. Big stuff. Big stuff. Jeez Louise!
So they had these really rugged ice bridges to basically be a wall of protection to prevent different things from hitting the power cables and data cables going up the tower. This is looking from the bottom of the boom up at all the steel. There's the RU-32 again on the backside. You'll notice that there's a lot of supporting going on. Every so often, the jumpers have to be supported. That's actually a standard for the AT&T book. After the connector, the jumpers need to be supported within every 18 inches. So after every connector, like I said, our first support would be here, which is about 18 inches from the connector. And then after the first support would be 3 feet. So every 3 feet after needs to be support. So you have here, this is about 2.5 feet, 2 3/4 of a foot, and we have a support here, and then down here comes over, comes up and into the antenna, and again at the connector on the antenna side as well, within 18 inches it's supported and has to be straight directly. You don't ever want to stress out an RF connection or bend it in ways it was not intended to bend. This coax is LDF450A, which actually has a foam dielectric insulator in it. And the more you bend that cable, the more out of place and funky that foam starts to become, and you can actually create harmonics and all sorts of different issues with that. So you want to keep that to an absolute minimum. Okay, we didn't go over the panel antennas themselves. So inside these antennas, these are actually 2 antennas sandwiched together. This was released by CommScope with their new antennas out there to just, again, try to save weight up on towers in space. But this is a quad band antenna. This antenna will do anywhere from 1900 meg to 2300 meg. Additionally, it will do the low bands of 850 and 700. So the low band ports are on the outside. So this is the low band. These over here are the low band, and then everything between is the high band. Like I said, 1900 all the way up to 2300 meg. Inside these antennas, they are not vertical antennas inside. These are actually little tiny individual antennas, and there could be anywhere from 20 to 48 of these little guys. and they stand out. They point directly outside the antenna coming out this way, and they radiate different patterns that cover different angles. The different radiation patterns can be anywhere from 80 degrees to 130 degrees or 140 degrees. So they are pretty versatile in their radiation patterns. And additionally, they have an onboard computer inside these antennas called a tilt computer, and the tilt computer is tasked with tilting the beam, the radiation path up and down. And what that does is, if you have a area where you have a high amount of usage lower than your far out sites, you can actually tell the radio to tell that computer inside to bend the radiation pattern down a little bit, because these sites are up, anywhere from 300 to 400 feet up in the air. So if you just go straight out, you're going to be shooting over all of your customers. So you need to take into account the options to bend that radiation pattern down just a little bit, just to help serve most of your closer customers to the tower site. So the system that does that is called the RET, Remote Electronic Tilt, and that was a little motor in here, like I said, responsible for adjusting a metal rod in between the antennas. And basically they were adjusting the ground plane. That ground plane was adjusting the RF pattern and RF beam of the actual radiation pattern of the antennas. So speaking of radiation, I do want to say again that the radiation is dangerous up on towers, and it's something a tower climber has to take into account. However, there's been a lot of things online saying cell sites are really dangerous, cell sites output so much radiation. That's not necessarily true. You're only going to be having exposure symptoms if you're within 5 to 10 feet to 30 feet of an antenna. Any further out, for example, a house on the ground versus a tower 100 feet, 200 feet up in the air, isn't going to have any issues. The RF radiation is so low, you wouldn't even notice it, and you really are not going to be having any significant health effects from that. I mean, there's a lot of people saying out there that the 5G is giving crazy issues and this and that and the other. No, it's absolutely false. You are not going to be getting RF exposure or any actual RF symptoms unless you are literally working up on the tower or you are working in front of the antenna. So there's a lot of different symptoms out there. I'm not a doctor, so I'm not going to say what those symptoms are. I would recommend, if you're interested, to look those up, but that's just something to note, that these antennas are, while they are very powerful, they do not output more than 80 to 100 watts per band, and the thought of somebody getting RF radiation sickness from a house location or on the ground when this tower is 100 feet up in the air is just absolutely untrue. So that's not an issue. Um, but that being said, when I was up on a tower, when my early years in the industry, we actually had to have little RF dosimeters that would, or EMF detectors that would tell us what our rates were. Another thing I'd like to clarify is cell site RF radiation is not nuclear radiation. They're two complete different radiation types. The cell site is non-ionizing radiation, which means it's just a RF system that's transmitting. Nuclear radiation, like from uranium or fallout, is ionizing radiation, and that is way, way, way more dangerous than non-ionizing radiation. Okay, now we are in my personal favorite part of a cell site. We are in the shelter. This is where all the magic happens. A lot of cool stuff happens up on the tower top, but I prefer the shelter. So we'll start from right to left. On the right, we have our Emerson power plant. This is a NetSure system, and these are really, really versatile products. I really love Vertiv. I love working with that company. Their customer service is great. Their engineers are phenomenal. They're always there to help you and excited to help you with your issues or on-site problems, or they even have great advice on purchasing equipment and buying different equipment for different systems. So they pretty much sell everything power-wise. But for this example, this is a DC power plant The role of this is to rectify and convert AC, alternating current, into DC, direct current. And it does that by these little modules here called rectifiers. And these are actually responsible for rectifying the 240 volts AC into 48 volts DC. They're modular, they can be removed, they can be added, and the controller controls all of them in a series and will automatically transfer load to one versus the other. And then the other nice thing about these new systems is if the cell site doesn't need to have all the rectifiers running to maintain the load, it doesn't do so. It will actually shut down the system. It'll put rectifiers to sleep, and once they've been put to sleep, they are in standby mode, waiting to get turned on when the load increases, and it just turns on the rectifiers needed. Below that are batteries, and the batteries are responsible for keeping the cell site on while the generator kicks in. The batteries are not designed to keep the cell site powered up when there's no power whatsoever. That is kind of a misconception. There are cell sites out there where batteries are the only line of defense for a power outage, but you would see much, much more batteries on a cell site than what we see here. So these batteries are SBS types, and they are 170 amp hour at 12 volts per unit. They are about 100 pounds a piece, and they are huge, huge batteries. Um, and like I said, they are not designed to take the full load forever. They are designed just to be as a little cushion there while the generator kicks back in and powers up the rectifiers. Okay, so we're going to power this side up. We're going to see the rectifier lights turn on. I'm over here flipping breakers on. Um, and we'll get into how this works a little bit more in depth here. Now I'm turning on the batteries, putting them in phase or in the system so the power plant does not start complaining and telling me I have an alarm on battery disconnect. Okay, so these are three different buses. We have the A bus, B bus, C bus. A bus is on the bottom, B bus second, C bus top. These two buses are 48 volt only. The bus on top is 24 volt, and 24 volt is kept just in case there's equipment on site that uses 24 volt DC. Sometimes most of that equipment's getting phased out, but you'll see the occasional microwave system that uses 24 volt. But like I said, it's not necessarily a system that's kept anymore. So 24 volts not widely used. We just use the two main 48 volt buses. Okay, so on the second bus here, you'll see a line of breakers. The breakers are exactly what they sound like. These are just little disconnects that disconnect circuits if they exceed a certain amperage, and I think these particular breakers are like 30 amps. And then next to the left of it, we see a blue breaker looking system. So remember how I said that the original radios were pulling, the newer radios, the white combo dual radios, were pulling a lot of power. That actually started an entirely new issue in the industry. So for anybody that knows anything about DC voltage, DC is extremely lossy at long runs. So you got to take into account when we run a DC power trunk up a tower, we're running it anywhere from 80 feet, 50 feet, all the way up to 500 feet going up the tower. So you can imagine how much loss that has of DC voltage going up that trunk. So when we put these new radios up and started turning systems online that ran these new dual band radios, these radios were drawing almost 50 amps on the DC side per radio. So what that was doing is the radios are supposed to see at least 48 volts, but the radios were actually getting dropped down to 48 volts or 42 volts, and in some cases as low as 36 volts. And 36 volts is not going to turn the radio on, let alone 42 volts. So what Vertiv did is they designed a little product here, which is basically a step-up DC converter that would convert the 48 volt coming out of this bus bar, and it would step up the voltage to about 56 to 58 volts, and somehow they would be able to take into account what the tower top voltage was at the radio. So these little guys have a little microprocessor in them that would see the fluctuations and would drive the voltage up depending on the demand at the time. So if the radio was seeing 42 volts, the uh, step up here would actually step it up to about 56 volts to accommodate for the loss in the cable. And these were a brand new product in the industry. They came out to accomplish that step up issue. So I think they're still used. I'm not 100% sure. If somebody knows more about that, let me know. Below is the controller. This is the controller that controls the power plant, the alarms, the power consumption, reports power, issues, and all that to a central controller. So get a big display here. This basically showing that, hey, I'm on AC power, my system is good, there's no alarms, I'm not on battery draw. Shows the float charge, capacity being used, which is pretty much zero, and also shows the amperage being used. And then this system floats at 55 volt, and what that means as the rectifiers are floating the batteries at 55 volts DC, and that just helps them to top off and to keep them energized at 100% in the event the rectifiers get cut off and die out because AC grid power gets disconnected. Alright, so this is just the exact same thing as what we saw up on the tower like the Squid. This is the lightning arrestor, and this is responsible for arresting the shelter portion or the shelter side of transient voltages that may harm the power plant or other equipment on the site. So like I said, these will divert any stray voltage that exceeds, I think it was anything above several thousand volts will immediately be diverted from the power trunk coming into the shelter off the tower to the ground directly, and it does that through a strike zorb technology, and I'm not 100% sure how those work or how they perform. So another one of those things, if anybody knows info about that, just tell it in the comments. We'd love to hear more about it, how it works. The green lights just symbolize that, hey, I have voltage, I have 48 volts. It's wired up correctly as far as polarity is concerned, so that is just saying everything's good to go. Okay, these are the back side here. This is the 48 volt DC cabling. The gray is going to the power plant. This is called Telco Flex. And then the red is the power trunk going up the tower. You'll notice that this here is blue, this here is orange, and then this here is green. And that would symbolize what sectors that these are going to be used for. In the industry, we use a lot of wax stringing. This is my wax string work. And then these are the power trunks as well that are getting ready to go out their way to the outside up the tower. This is just kind of what it looks like on the inside. And we have a ground bar. The ground bar on the other sector or the other site. Go back to it here. This is the ground bar that is every rack has a ground bar. That ray cap is grounded to a ground bar. And then the ground bar has a additional stinger that joins this with the main ground bus in the site for the main ground bar. Up here, this is the far left rack. This is the rack that is responsible for all of the fiber optic routing and the actual data portion of the site. So up here is a DC power distribution unit. This is all 48 volts. We have our 48 volt from the power plant, and then we have 48 volt supply. These are protected from the breakers, and these are just little, they call them grasshopper breakers or grasshopper bus fuses that will actually break and indicate an alarm when they make contact when a short occurs. This here is the cell site router. This is an ASR 9300 model, and this is just responsible for overseeing the basic routing protocols on a cell site. They only use fiber, they don't use the Ethernet ports for anything. The fiber is over here. All the fiber optic connections are LC. This is a fiber optic patch panel. This is kind of a rarity to have on site. Normally you didn't see these a whole lot. But the way that these work is pretty simple. The fiber optic cable, the trunk coming from the tower, would plug into the back of this, and this would be where the connections are made from the fiber trunk to the actual baseband unit that controls all of the radios on the site. This is a little storage tray, and this is just kind of where fiber optic patch cables are stored. You don't want to store fiber optic in the vertical managers. That's actually a big no-no in the AT&T handbook. Fiber is supposed to be coiled neatly in storage trays. It's the only approved place they can be stored. Okay, so these are the Ericsson baseband units. These are the units that are controlling the radio, the LTE, the phone calls, the data, the voice, everything on a cell site. This is the heart of the data system. So we have fiber optic. Each fiber optic cable is coming from the radio up on the tower we saw earlier. And we have two different units here. These are different generations. This is the older generation. This is a 5216 Ericsson baseband unit up the top here, and then the bottom is a newer model. I don't remember off the top of my head what model these are, but this is the newest, latest and greatest, best of the best from Ericsson, and these are designed to be compatible with just about any Ericsson radio out there. It's all proprietary software, and we could go over that at a later date, but this is just kind of a basic on how the Ericsson systems look. And you'll notice here that they have a sync light. You can't read it, but that says sync, and that is where the cell site gets its GPS from. This actually goes to a GPS little, I call it a brick because it looks like a brick, but it goes to a GPS brick, and then that goes outside to a GPS antenna, and we'll go over that later. On the right here is where the DC comes from the power plant. This is the power bay, or the shelf that holds the older style Ericsson units, and then they have a clock that plugs into the side. So the older units are actually capable of holding two baseband units, but even with two baseband units, you are only going to have 6 ports total for each carrier. So it was kind of getting annoying having to have all these little things on site when they could just make a bigger platform like this bottom one and carry a lot more traffic and be able to provide for a lot more radios with less equipment. So again, smaller was the name of the game, and this is what they're going to. Okay, below that is a Nokia baseband unit, and you're never actually going to see a combination of Nokia and Ericsson equipment together. They're actually completely separate ecosystems. And they are you will see Nokia on the eastern side of the United States, whereas you'll see Ericsson mainly in the southwest and western part of the United States and central. So Ericsson has a little bit more coverage to deal with than Nokia, but they're both pretty good systems. I personally like Ericsson better. I just think it's a better equipment and it's just easier to use. I have a question for anybody watching the YouTube video here, but on the Nokia baseband units, they have HDMI ports on them. The HDMI ports were used for GPS sync systems, and I would love to know why Nokia decided to go with an HDMI connector and cable to control their GPS systems. So if anybody has any information on that or any input on how that works, or why they went with HDMI, I would love to know more, and I'm all ears. Put it in the comments. Okay, then we move over to the quality of service switch. Not all cell sites had these, but most did. This is really just serving one purpose, and that is to guarantee quality of service from the backhaul to the cell site and vice versa. This just makes sure that the backhaul isn't having dropped packet issues, and it is kind of just like a referee making sure that all of the internet protocols and IP protocols and tables are doing what they should. Okay, so this here is a TV screen hooked up to a small computer, and this TV screen this system was designed to give people a in-depth look at a cell site, troubleshooting how to plug in and configure systems in the Ericsson BBUs, the Nokia BBU, and the Netsure 70 Netsure Vertiv power plant. Configure all that and get it alarm-free, and a great way to teach people how to look at alarms, clear alarms, and just how to interact with a cell site in the real life situation. And again, giving them every best tool possible to run the cell site. So this computer was actually wired in directly to um, all of the equipment on the site, and that's not something you normally see on the cell site. There's no like central computer there to check everything. This is just a added bonus for learning. Okay, so this is a outdoor cell site. This is what you would see on a more of a modern day cell site. AT&T doesn't do the big indoor cell sites anymore. They just kind of take up a lot of lease space, and they cost quite a bit of money to operate with air conditioning. It's a lot cheaper to have little parcels and outdoor lockers, and they just have everything sitting inside those lockers, and then they're cooled by ambient temperature. They're not actually air conditioned anymore, so they just pull in ambient air and they cool it, and it's pretty interesting to see something intake, Texas summertime, 105-degree weather, and it works just fine and doesn't mind it at all. So it's pretty remarkable equipment to be able to achieve that. This guy right here sitting behind the handrail is a quality of service switch. This is just rated for outdoor, but it's the same thing as what we saw on the other indoor shelter. Alright, so I'm going to go through and power all this up. I'll just go ahead and fast forward to the power plant turning on. Just give a little bit of mindful here. This has got a lot of fan noise. These are really big fans that are moving some air, so this thing sounds like a damn turbojet engine when it fires up, so just watch your headphones. So power plant turned on. It's the exact same power plant as the power plant in the indoor shelter. It's just condensed down to 2 buses instead of 3, and it is all compact and just very, very tight quarters. So you still have a battery bank below it, still this 3 levels of batteries, and it does the exact same thing as the other power plant. It's just in an outdoor cabinet. This is the outdoor baseband unit cabinet. So just like the rack in the indoor shelter, we have the exact same stuff going on here. We have the indoor or outdoor cabinet, and inside of it is the same exact baseband unit along with the ASR 900 router, along with the GPS equipment and the fiber optic trunk coming back down. This gives you a really good look at what it looks like on the indoor side. So it's a pretty good little sneak peek at how everything kind of just works together, and it's just about to fire up. So a really important part of the cell site that doesn't get a whole lot of credit is the GPS. This little antenna up here is a GPS antenna, and that essentially tells the cell site where it is and where it lives. The cell site will not work without a GPS sync. The reason it doesn't work is it has to know where it is in order for it to talk to you. So let's use the example of you're driving down a highway and you are on cell site A, but you are approaching cell site B, C, and D. Um, Within those cell sites, they will automatically talk to each other and they'll talk to your phone, and they will automatically decide, hey, your phone can connect to B, C, and D cell sites with no problem, but because the lat and longitude of cell site B is closer, we are going to connect you to that cell site because C and D are actually a little farther. So the GPS system tells the cell site, like I said, where it is, and that's how it essentially matters when it's communicating with the phone, and that's how it routes your phone and allows your phone to make the decision to connect to the best optimal signal and cell site closest to you. These are the exact same. This is the DC-12. This is the exact same as the indoor unit. This is just an outdoor box, and instead of mounting it in a rack, it's mounted on a box on the side of a handrail or the unistrut. And it's the exact same thing. Once again, you got the rubber wires going to the power plant, and then you have the red and black wires going to the power trunk and then going up the tower. And this is a special thing that was featured in one of my older YouTube videos. I will link that in the description. But this is a tower light beacon that was given to me by a person on site. They were getting rid of it and they were going to throw it out, so I decided I'd take it home. And they also were going to throw out the driver box, so I have the driver box and the light itself. And it was featured, like I said, in a YouTube video. I did a lot of cool lights with it. You can actually see what this thing looks like full power inside my garage. So if you guys want to check that out, link in the description. Pretty neat little setup. Anyway, this is pretty much vital. Most towers have beacon lights at the top, and this was just another reason to make it as real as we could. The reason we had this light on the top of the tower is because we wanted to show that no equipment under any circumstances was permitted to be higher than the beacon light. The beacon light always sits higher than the equipment on the tower, and that is an FAA mandate. You have to have it that way, so it's just the way it is. But the cool thing about this tower top beacon was it was never turned off. Once we put it on and left it on, this thing stayed on 24/7, and it was just pretty neat to see it blink when everybody was going home and the warehouse was pretty much getting dark for the day. It's pretty neat to see something like that up on the tower on a project I built. So cool. I know that was a long video, guys, and I apologize for it. You guys wanted a commentation, so here you go. I appreciate you if you made it this long into the video, how it works, then hats off to you, because I know that's a lot of information to take in. Um, so yeah, there's a lot of equipment going on in a cell site. Again, I just want to reiterate that cell sites are actively monitored. Do not trespass on a cell site. It's actually a federal offense. It's a felony immediately. Felony trespass, and it's just bad. Don't trespass on a cell site. Um, if you see a cell site driving down the tower, look at the tower from a distance. Don't approach the cell site. They can be dangerous places too. I've had a lot of examples of that in Houston, St. Louis, where you have homeless living on cell sites. Tweakers are there. Sometimes there's even people living in the shelter. It's just not a good thing for anybody. So stay away from them. Give all the wireless carriers, their needed security for this stuff. But I do encourage everybody to be curious. Ask questions. If anybody has additional questions on how any of this equipment works or any input, I'm all for it. I appreciate it. So, just to reiterate some things, cell sites are these towers you see all over the place, and each cell site has a bubble, essentially. That bubble is the range that cell site will take traffic in. Once you leave that bubble, you hand off to another cell site, and the bubbles are actually designed to cross over each other. Because if you have bubbles that end away from each other and you go in between that little valley or that space where there's no coverage, you'll have a hard handoff. And that's what's called a hard handoff, where you will have packet loss in a phone call. You'll be driving, your phone call may end, but it happens so quick that you don't even see it on your phone. It just looks like, oh yeah, I got normal service. There's nothing wrong. Um, that's the hard handoff, and that's what AT&T, Verizon, T-Mobile are trying so hard to mitigate, is that hard handoff between sites. And they do that by building more sites, building better radios being manufactured and invented, new technologies being invented. This video is old. I'm coming out with this video today, September 24th, 2024, but everything you saw in this video is most likely already obsolete. That's how fast the industry moves. We would upgrade sites every 4 to 6 months. It's miraculous how quick technology moves. So these big telecom companies are staying on the edge of cutting technology. They're doing everything to make sure that they can guarantee customers with the best service. There's debatable service depending on different carriers. Some carriers have better service coverage than others. Some have worse. It just depends on where you're at. But I'm telling you, they don't do that by choice. There's other things that limit them, like landlords that don't want them to build towers around. High cost of tower leasing, which AT&T is actually back in the process of building their own towers in some cases. So they kind of went full circle from what they did. But that's everything in a nutshell, guys. I hope you guys appreciate the video. I don't often like to recommend it. If you like the video, give it a thumbs up just because I'm trying to get a little bit more traffic on the channel. Things have been a little slow lately, so a thumbs up would be great. And if you have a comment asking questions, please, please, please put it in there for a comment asking a question. I'll do my best to get back to you on it. If I can't, I would appreciate if somebody else could comment and answer that. It would be great. And then even better, we have a Discord server. If you have questions, I can get back to you much quicker on the Discord server than I can on YouTube comments. So it's just kind of a better of two evils. But the Discord is much better. I'm in there almost every night. I try to jump in there and we work on different server problems, different stuff. Doesn't have anything to do with cell sites. But hope you guys found the video interesting. This is Accomplish the Impossible out.